As the Earth goes round, you may have thought about our planet and what it needs most, a more sustainable future for everyone. And that's what everyone wants, including our friend Kim. Nothing like sleep to recharge the batteries. Freshwater reserves are increasingly scarce on the planet and in Kim's home. And saving resources isn't exactly his strong point. From the looks of it, food resources are also scarce here. It's time to think about resupplying. And it's difficult to choose from so many options. You may think that this yogurt container has a very short life between the supermarket and the trash can. But who said that's how the story ends? And who said the supermarket was the start? There have already been many phases in this product's life cycle, and many more are still to come. To better understand how this works and its impacts, a very efficient tool exists: the life cycle assessment. You want an example? Let's analyze the cycle of the very same yogurt pot. Everything starts with the extraction of the raw materials. Among other things, oil is used to make the plastic pot that will protect its contents. There's also the milk used to make the yogurt, the strawberry for flavor, the aluminum foil lid to seal in the product. There's lots of different processes. And each one has various kinds of impacts on the environment. And the cycle is only just beginning. At various moments, there's need for transportation. Then there's storage and distribution. It's a long ways to reach the consumer. And like I said before, the story doesn't end with the trash can. The pot can be recycled and used to make a new product, with the cycle restarting, or more precisely, continuing. LCA provides a rigorous analysis of the environmental impacts of all stages of the production process. This analysis helps manufacturers make decisions that help improve processes, products, and services. As you can see, every element of the universe, including ourselves, has a life cycle. Now that you've seen how it works, you won't be able to resist paying attention to the life cycle of every little thing around you, and to compare the impacts that each product has in order to make conscientious choices.
Society faces important environmental challenges. Greenhouse gas emissions increase the Earth's temperature. Industrial pollution and toxic emissions endanger ecosystems and clean water reserves. Important metals needed for electronics and machines are becoming scarce. Fossil fuels, which society heavily depends on, are rapidly depleting. Solving these environmental issues increasingly becomes a responsibility of the producing industry, since it is a main origin of these environmental problems and a large consumer of fossil fuels and mineral reserves. To understand to what extent an industry contributes to various environmental issues, products can be screened using life cycle assessment. This is a technique to assess the environmental impact of a product's life cycle. In life cycle assessment, all stages of a product's life are taken into account. Resource use, material processing, product manufacturing, distribution, use of the product, and end-of-life operations. Life cycle assessment has been standardized by the International Organization for Standardization and gives us the opportunity to measure how the life cycle of a product contributes to an extensive set of environmental indicators. These are grouped in damage to human health, damage to ecosystem quality, and resource depletion. This way, products can be compared by using specific environmental themes. This allows us to answer questions like, which product has the lowest impact on climate change? Or, which product is most toxic to humans? Life cycle assessments shows in which life cycle stage environmental impacts are highest, and can even assess individual steps in the production process. This way, companies can decide how to improve the environmental performance of their product. Results can be used for marketing purposes, like product A has a lower environmental impact than product B and C. Or, for R&D, we know how we can improve the sustainability of this product. Sustainable development is the most important challenge of the future, and life cycle assessment gives important conclusions on how to make industries more sustainable.
For more information, please contact Dr. Lex Ruse.
Life cycle assessment is a technique used to assess the environmental impacts associated with all stages of a product's life. The three main features of any life cycle include a product's manufacture, its use, and its disposal. But there are sometimes other stages, which we will consider later. Why do you think it is important to consider these aspects when making a product? When a device is manufactured, the materials it's made from can have a huge environmental impact. With the wide-scale use of mobile or cell phones since the 90s, not a lot of thought went into the materials used to make them. Now huge numbers of these phones are found in landfill sites. Mobile phones are made of 40% plastic, 40% metals, and 20% trace and ceramic materials. The materials used to make mobiles weren't ready to be used by manufacturers. This means they had to come from somewhere. Have you got any ideas where? Some suggestions would include crude oil, which is used to make plastic casing, or the metals, like copper, used in this circuitry. Also, when making the display and the rechargeable batteries, other metals also had to be mined. In doing so, vast amounts of energy were expended. Mobile phones have 8 life cycle assessments, one for each component. These include the printed circuit board, the display, the battery, the keypad, the microphone, the speaker, the plastic casing, and any accessories. Now we're at the manufacturing stage of the life cycle assessment. Mobile phones made in the factories require a great deal of energy to create. It is estimated that during manufacture, a single cell phone uses approximately 1,390 millijoule of energy and produces 60 kilojoule of carbon dioxide emissions. Many products require the use of packaging as well, to prevent spoilage, damage, contamination, and tampering. By considering the materials these phones are made of, or reducing the number used in their manufacture, this can lower some of the energy requirements. The next stage in the life cycle of a phone is its packaging and transportation. Packaging consumes valuable natural resources, such as paper from trees, plastic from crude oil in the earth, aluminium from ore, or other materials, all of which use energy to extract and result in waste. Although some packaging can be made from recycled materials, in addition, the transport of phone by plane, truck, rail, or sea all require use of fossil fuels for energy and contribute to global warming. Next, when making a mobile or cell phone, the environmental impacts during its useful life also have to be considered. The environmental impact of a phone is lower than, say, of a car, which burns fuel for its entire life. However, the lifetime of a mobile or cell phone is estimated it's only between 18 to 24 months. This means that existing phones are exchanged for newer models, so more and more old phones are being dumped. One way to extend the useful life of your phone and prevent waste is to use the same phone for as long as possible. When you shop, try to make sure you get the service and the phone that's right for you. Inevitably, each phone will come to the end of its useful life. This is the last part, the disposal stage of the life cycle. How do you think you can dispose of your phone more responsibly? Some ways would include the reuse of your phone. Just because you may have finished with it, if you donate it to another family member or to a charity, the phone will.
What is a life cycle assessment? You might know it as an LCA. You also might know that it's a kind of tool, a model for analyzing environmental impact. But what makes an LCA so useful? Let's say you've just developed a brand new product. You're really proud of it, and you know your customers are gonna love it. But maybe the production process isn't as great as it could be. Trying to solve complicated issues like these can be pretty challenging. Luckily, LCAs can help us understand how all of the parts move together. The methodology of life cycle assessments asks us to apply both qualitative and quantitative analyses. On one hand, this means we can get a broad overview of the production and environmental factors we want to target. On the other hand, applying numerical methods to our model means that we can also target the depth of detail we want to achieve. Life cycle assessments can vary in how they are implemented. They have been standardized under the ISO 14040 family, a non-compulsory set of standards that describe their purpose, framework, and methods. This is an important point to remember. The phrase life cycle assessment describes a model for analysis. No two LCAs will look quite the same. Maybe you've made your product more recyclable and just want to re-examine the end of its life. Or maybe some new legislation gets passed and it forces you to rethink your entire supply chain. Once we've determined our scope and our purpose, we can begin performing our analysis. A typical LCA has three main parts. The inventory analysis lists all the inputs, intermediates, and outputs associated with a product. This includes all flows of energy, resources, and wastes. The impact analysis quantifies the items in this inventory. Common parameters include cost, carbon footprint, and volume or mass of waste byproducts. This is a particularly important step that requires foresight, creativity, and strong attention to detail. Finally, the improvement analysis consists of strategies to optimize your production. A well-executed LCA has a good chance to result in measurable, attainable goals for improving flows and mitigating environmental impact. If you have a product that needs assessment, here's some examples of things you'll need. A bill of materials with as many supplier details as you can collect. Shipping and packaging information, including the cost of warehousing and internal transport. Channels for the product's end-of-life phase. This means any plans in place for recycling, recovery, and disposal. Are you ready to learn more about lifecycle assessments and ISO 14040 compliance? Contact EnviroPass today for your free consultation.
With all the decarbonisation talk, every business leader really must know what to consider as part of their company's carbon footprint. We tend to think about facilities, the energy usage and perhaps the fleet, but these only account for a part of companies' total carbon footprint. To help you better understand this, let me walk you through the concept of Scope 1, 2 and 3 emissions. I'm the sustainability speaker, Susanna Hasenöl. Scope 1 and 2 emissions arise from a company's operations, such as production facility or heating or cooling the office. These are somewhat easy to control, for instance by switching to renewable energy or to an electronic fleet. But what about Scope 3? Oh, that is a nice cup of tea. Pukka, a Unilever brand, reports that 49% of their emissions come from boiling the kettle to make a cuppa. This is an example of Scope 3 emissions, which are more indirect, yet related to the usage of a company's products or services. Often, Scope 3 makes up most of a company's carbon footprint. Scope 3 can be difficult to measure as it includes emissions from waste when a product is disposed, the supply chain, outsourced activities, as well as things like business travel. When you come across with a company's carbon disclosure, do ask whether it includes Scope 1, 2 and 3. Thanks for joining, and let me know if you'd like to learn more about business climate matters. I'm Susanna Hasenöl, the sustainability speaker.
What are ecological indicators? Ecological indicators are organisms, that is, living beings that give us data about an ecosystem. Typical data that scientists gather from ecological indicators is, for example, an ecosystem's biodiversity. We use these indicators to measure our impact on certain ecosystems. There is growing interest worldwide in our impact on the habitats of animals and plants. Beetles may be used as ecological indicators. Perhaps I want to find out about the state of an area of agricultural land. One way is to gather as many different types of beetles. The variety could be compared to another area of farmland or the same area 20 or more years ago. We can also use lichens as indicators of air pollution. Lichens are slow-growing plants that create a crusty growth on trees, walls, and rocks. Fossils can serve as indicators of past environments. This is useful if we want to find out how an area has changed over millions of years. Ecological versus environmental indicators. Do not confuse these two terms, their meanings are completely different. An environmental indicator is a measure, a numerical value, that gives us information about our environment. For example, a graph showing how average atmospheric temperatures have changed over time is an environmental indicator. Thank you for watching this brief video on ecological indicators.
So we've been looking at the operation of a sawmill, how we would do an analysis in order to produce an LCA of maybe producing 1 cubic metre of sawn wood. But that sort of analysis, if we're looking at the whole process or the whole life cycle of a product, that part, the production side of the process, which includes the forestry operations, that is what's called cradle, which is obviously where something's born, in our case the forest, to factory gate. So that analysis only considers the first part of the life cycle. But if we want to do a full, If we want to do a full life cycle assessment, then we have to consider other parts of the life cycle as well. So we're going to take the wood and we're going to transport it maybe to a construction site. So in that case, we have to look at the construction process, the energy that's involved in doing the construction, and maybe the other materials that go into producing a product that's used in a building. Maybe we're looking at a window or cladding or something like that. There may be other materials like paint or screws or other materials that are going into that product. After the construction part, we have the in-service phase, the life phase of that product. And whilst it's in service, there may be maintenance that we do. We might be painting the window or the cladding, or we might be maybe even replacing some parts over the lifetime of that particular product. And that product may be in service for 60 years or 100 years or 50 years, and we have to take that into account. We have to decide how long our analysis is going to go for. At the end of life, then we remove that product, and then what's going to happen to it? Is it going to be reused in some way? Is it going to be recycled? Maybe the wood that we've used in the cladding is going to be chipped and used in particle board, or maybe it's going to be incinerated and used for energy. So we have to consider that as well. So this would be the full life cycle. And eventually, of course, we've started at the forest to produce this wood. And eventually, of course, at the end of life, if we did incinerate, then that carbon dioxide from which the wood was made in the first place will be returned to the atmosphere, and then eventually it will reappear in trees that grow in the forest. So the whole process that's going on here really is sometimes called follow the atoms.
This is the story of 3 plastic bottles, empty and discarded. Their journeys are about to diverge, with outcomes that impact nothing less than the fate of the planet. But they weren't always this way. To understand where these bottles end up, we must first explore their origins. The heroes of our story were conceived in this oil refinery. The plastic in their bodies was formed by chemically bonding oil and gas molecules together to make monomers. In turn, these monomers were bonded into long polymer chains to make plastic, in the form of millions of pellets. Those were melted at manufacturing plants and reformed in molds to create the resilient material that makes up the triplets' bodies. Machines filled the bottles with sweet, bubbly liquid, and they were then wrapped, shipped, bought, opened, consumed, and unceremoniously discarded. And now here they lie, poised at the edge of the unknown. Bottle 1, like hundreds of millions of tons of his plastic brethren, ends up in a landfill. This huge dump expands each day as more trash comes in and continues to take up space. As plastics sit there being compressed amongst layers of other junk, rainwater flows through the waste and absorbs the water-soluble compounds it contains, and some of those are highly toxic. Together, they create a harmful stew called leachate, which can move into groundwater, soil, and streams, poisoning ecosystems and harming wildlife. It can take bottle 1 an agonizing 1,000 years to decompose. Bottle 2's journey is stranger, but unfortunately no happier. He floats on a trickle that reaches a stream that flows into a river, and a river that reaches the ocean. After months lost at sea, he's slowly drawn into a massive vortex where trash accumulates, a place known as the Great Pacific Garbage Patch. Here, the ocean's currents have trapped millions of pieces of plastic debris. This is one of 5 plastic-filled gyres in the world's seas, places where the pollutants turn the water into a cloudy plastic soup. Some animals, like seabirds, get entangled in the mess. They and others mistake the brightly colored plastic bits for food. Plastic makes them feel full when they're not, so they starve to death and pass the toxins from the plastic up the food chain. For example, it's eaten by lanternfish. The lanternfish are eaten by squid. The squid are eaten by tuna. And the tuna are eaten by us. And most plastics don't biodegrade, which means they're destined to break down into smaller and smaller pieces called microplastics, which might rotate in the sea eternally. But Bottle 3 is spared the cruel purgatories of his brothers. A truck brings him to a plant where he and his companions are squeezed flat and compressed into a block. Okay, this sounds pretty bad too, but hang in there. It gets better. The blocks are shredded into tiny pieces, which are washed and melted so they become the raw materials that can be used again. As if by magic, Bottle 3 is now ready to be reborn as something completely new. For this bit of plastic with such humble origins, suddenly, the sky is the limit.
Today, the world produces over 2 billion tons of solid waste yearly, and that amount is expected to grow to 3.4 billion tons by 2050. About 1/3 of that waste is not managed properly. Hi, my name is Jeremy Gregory. I study the economic and environmental implications of engineering and systems design decisions, particularly in materials production and recovery systems. My research topics include product and firm environmental footprinting through life cycle assessment, manufacturing and life cycle cost analysis, and characterization of sustainable material systems. Life cycle assessment is an approach to quantify the environmental impact of products and processes throughout their life, which can include material extraction, manufacturing, use, and disposal. The course serves as a starting point for conducting and interpreting a life cycle assessment in accordance with the methods and policies defined by the International Organization for Standardization, or ISO. This course includes the stages of goal and scope definition, inventory, impact assessment, and interpretation. Learn to conduct a life cycle assessment and analyze others to support informed decision-making. We designed this program for professionals from a multitude of backgrounds interested in sustainable actions and innovation opportunities. Those who will benefit the most from the skills and expertise that this program offers include consultants of companies who must be aware of current sustainability policies and how to enact them within an organization, companies and industries concerned with meeting or setting carbon targets or hoping to reduce their impact on the environment, data scientists, engineers, and scientists involved in conducting and interpreting LCAs, accounting firms tasked with reviewing and auditing corporate greenhouse gas emissions and estimates, and legislators and policymakers creating and implementing policies about sustainable products and processes. Life cycle assessment is an increasingly important